This is Janet Hildreth, MRI 2330 week 5 homework. The topics I'm supposed to be discussing today are fast spin turbo echo, incoherent gradient echo, and fast gradient echo. So I'll start with fast spin echo or turbo spin echo. These sequences are most commonly used sequences in MRI. They're based along with the same concept of spin echo sequences, and their diagrams are somewhat similar as well. The difference between fast spin echo and just a traditional spin echo are the scan times and the additional 180 refocusing pulses between the 90-degree RF pulses. These additional RF pulses have an advantage in imaging because they're able to cover K-space with multiple phase encoding lines with a single excitation. The number of 180-degree refocusing pulses is called the echo train length or the turbo factor. It plays a significant role in image contrast and image quality. The number of 180-degree RF pulses performed per TR is the number of echoes produced within the number of lines of K-space filled. So at each rephasing, an echo is produced and a different phase encoding step is performed. The data collected from each echo is placed into one image. So the higher the turbo factor, the shorter your scan time will be. In order to fill out different lines of K-space, a different amplitude of phase encoding gradient slopes are applied at each 180-degree RF pulse phase encoding combination. Because echoes are generated at different TE times, the data collected has variable weighting. As a technologist, you can control the TE for the desired weighting. From here, the imaging system applies either steep or shallow slopes to various echoes to obtain your weighting. Steep phase encoding slopes reduce the amplitude of the echo, where shallow slopes have an echo with maximum signal amplitude. Maximum signals are centered around the effective echo time selected. Steep slopes are placed farther away from the effective TE. The data collected around your effective TE has more impact on contrast since they fill the central lines of K-space provided by echoes with the greatest signal amplitude. Data from these TEs not close to the effective TE fills the outer lines of K-space because of smaller echo signal amplitude. So we come over here to my diagram. These small boxes represent your 90-degree RF pulse, and these are your consecutive 180-degree rephasing pulses or refocusing pulses. So the time between these two is your TR. These is your phase encodings. So you can see where they are sampled at different amplitudes and how the signal, the echo signal, is produced. So at the steep gradients, you get a shallow, the shallow echoes, and then at the shallow gradients, you get the greatest signal. So what are some advantages and disadvantages of fast spin echo? Advantages is overall good quality images, optimal signal to noise and contrast to noise ratios. It is possible to obtain T1, T2, and proton density contrast much faster than conventional spin echo sequences. Your scan times are reduced, and which gives the susceptibility of artifacts reduced with the higher echo train length factors. Some disadvantages is image can appear more blurry than in conventional spin echoes because of the long echo trains. Flow and motion effects are increased, incompatible with some imaging options, and T2 weighted fast spin echo images show bright fat signal rather than darker fat signal due to the J coupling effect. So moving on to incoherent gradient echo, I felt that in order to talk about that, you first have to clear up what gradient echoes are. And even though gradient echo and spin echo sequence diagrams look similar in terms of their sequence structure, there is a striking difference which makes it easy to know which one you're looking at. The difference is the lack of the refocusing 180-degree RF pulses. Also, the initial excitation RF pulse that has a flip angle that is equal to or smaller than 90 degrees. So in the gradient echo sequence, the first negative gradient X line dephases the MR magnetic vector in the transverse plane. This is the dephasing gradient. Directly after the dephasing gradient, a positive gradient is applied to refocus or to rephase the MR spin to create a gradient echo at the TE. The GY, or phase encoding gradient, is to create an echo line in the K space, and the GZ, or slice select, is designed to excite a single slice of interest during the initial RF pulse. Now that we know a little bit more about general gradient echo pulse sequences, we can understand what goes on in incoherent gradient echo, or also known as spoiled gradient echo. These sequences begin with a variable flip angle excitation pulse and use gradient rephasing to produce a gradient echo. There remains a balance, if you will, of transverse magnetization from previous repetitions. These sequences dephase or spoil the magnetization, and since the transverse magnetization is what's being sampled, a T1 contrast image dominates. Because of the short TE that we are used, we do not have to wait for the 180 degree pulse and rephasing. That means that there's a short TE and a short TR, which equals a T1 weighted image. There are two ways to achieve this spoiling. One is the RF spoiling and one is gradient spoiling. In RF spoiling, the RF is transmitted at a specific frequency to excite a slice at a specific phase. Only frequencies from these echoes of the excitation pulse are digitized. Because the TR is short, there is leftover transverse magnetization that is not being sampled. And that balance has little impact on the contrast. Gradient spoiling is the opposite of rewinding. Rewinding is used in coherent gradient echoes, and remember that it is achieved by reversing the slope of the phase encoding gradient after readout, which keeps the residual magnetization coherent. In gradient spoiling, the slice select, phase encoding, and frequency encoding gradients can be used to dephase the residual magnetization so that it is incoherent at the beginning of the next repetition. Because of this, spoiled gradient sequences are mainly used to create T1 weighted imaging due to the reduced T2 start and T2 effects. These sequences are good to demonstrate anatomy and pathology after contrast injection. Another way that I had found to explain the gradient spoiling is that if you think of having a whiteboard that you filled all your information out and then completely erasing it, that's the applied or spoiled gradient at the end of class, which would be your end of TR, then the new class or the new lines being sampled will be fresh and clean. So it wipes out that residual transverse magnetization. So I have a small demonstration of this, of when you have it applied. So here you have this aligned along the transverse magnetization, and then you apply a gradient and it knocks it this way. You apply a gradient, it knocks it this way. You apply a gradient, it knocks it this way. And you wanted to get it, but when it's trying to get back to those places, there's that residual transverse magnetization, and those gradients just kind of knock it out of the way to be able to get a fresh signal when it changes its pulse direction. Okay? Some advantages and disadvantages of incoherent. Advantages is that it can be acquired in a volume or a 2D imaging. Breath hold techniques are possible. Good signal to noise ratio and anatomical detail in volume, and can be used after contrast injections. Some disadvantages is your signal to noise ratio is poor in your 2D images, and gradient noise is very loud. So our last topic is our fast gradient echo. Fast gradient echoes are particularly important because they can allow for very fast pulse sequences to acquire a volume in a single breath hold. They can use either coherent or incoherent gradient echo sequences but the TE is much shorter. Because you're only applying a portion of the RF excitation pulse, only a portion of the echo is then in turn read. This is known as partial or fractional echo. Also, some sequences use extra pulses before the pulse sequence begins to prime the system or to pre-magnetize the tissue. There are two ways to achieve this. One is an 180-degree pulse is applied before the pulse sequence begins, so the net magnetic vector of the tissue at full saturation is at full saturation and can either enhance T1 contrast or null the signal from certain organs and tissues. The other way is a 90, 180, 90-degree combo, which is applied before the pulse sequence begins. The first 90-degree pulse produces transverse magnetization. The 180-degree pulse rephases this, and the second 90-degree pulse is applied at a specific time, which drives the coherent transverse magnetization into the longitudinal plane to make it available to flip when the pulse sequence begins, because remember, in gradient echo it uses that flip angle. This method of priming is used to produce T2 contrast and is also known as driven equilibrium. Fast gradient echoes allow multi-slice gradient echoes with very short TEs. So multiple images can be acquired in single breath hold. Because things are going so quickly, the way the case space is filled will also be different. The possible ways depend on what you're trying to achieve in your image. There's centric filling, where the lines are filled linearly, but from the center outwards. The shallow phase encoding gradients fill first, leaving steep till last. Next, there's keyhole filling. This is similar to centric in that the K space is filled linearly, but the center lines are only filled during particular parts of the sequence, which is very important when contrast is being needed. There's single shot imaging techniques where there's the fastest scan time possible and all the lines are filled during one repetition. So all the data is collected from a single echo train. In order to accomplish this, the readout gradient must switch from positive to negative. Left to right equals positive and right to left equals negative. Also, the phase encoding gradient comes into play, filling positive lines, moving the K space, finishing with the negative lines. This is also called blipping. Lastly, there is spiral K space filling, and here the readout gradient oscillates to fill lines from left to right and then right to left. K space begins filling from the center. Phase gradients also oscillate to fill the line in the top half, then the bottom half of the K space. I hope that helps explain those topics. Thank you for watching.